Hello everyone, my name is Karam from the University of Balamand, Lebanon. In this presentation, I will be discussing how our proposed three-phase transformerless inverter is able to totally eliminate the common mode noise in photovoltaic grid-connected system. In the 21st century, the PV source becomes one of the propitious ways for power generation since it's not polluting, efficient, and climate-friendly. This idea is strengthened in this graph that shows the evolution of the annual global PV market in megawatt. As illustrated, the global market of PV systems is increasing continuously over the years. In specific, Lebanon significantly struggles in its electric power sector due to the power mismatch over the years between the production and demand. Unfortunately, since the power plants of Electricité du Liban are not able to assure a continuous supply of electricity, private diesel generators are used to cover the shortage in power generations. So in order to enhance its power generation and decrease the emissions of polluted gas, the country promised to profit from environmentally friendly sources such as PV. In the same context, a study was made to show the most reliable PV farms locations as shown in this map. Also, Lebanon can benefit from the wide range of PV applications and try to implement, for example, the grid-connected PV systems, which can provide a solution to overcome the shortage in power generation. In this type of systems, inverters are used as a connection point between the PV source and the grid. They are capable of converting the DC signal coming from the PV panels into an AC signal entering the grid side. Grid-connected PV inverters are divided into two categories: inverters with galvanic isolation and inverters without isolation. The galvanic isolation is provided by the transformer. However, these isolation transformers are massive, difficult to implement, and add extra losses to the system, which cause the overall efficiency to decrease. So in order to overcome these complications, transformers are eliminated. This fact will not only reduce the complexity of the system, but also decrease the cost and increase the efficiency. However, the absence of galvanic isolation causes a generation of common mode leakage current. To elaborate, this image shows a general model of a transformerless PV inverter system where the leakage current flows through the parasitic capacitance of the PV panel. This undesirable common mode noise can add losses to the system, cause electromagnetic interference, increase the output harmonics, and lead to safety problems. For the purpose of evaluating the leakage current issue, it is important to differentiate the concepts of common mode to differential mode. So given any circuit, the common mode voltage is defined as the average of the voltages from each output terminal to a common reference. For the system shown here, N is taken as the common reference. Thus, the inverter common mode voltage is given as follows. The differential mode voltage represents the voltage across the output terminals of the inverter, and it's characterized by the following equation. Now, based on the differential mode voltage, we can derive the additional common mode voltage. Consequently, in the equivalent common mode circuit, the total common mode voltage is obtained by adding these two voltages. This total common mode voltage must be constant without variation in order to suppress the leakage current. Therefore, researchers were encouraged to promote helpful transformerless inverter topology to achieve this goal. In single-phase system, some of the topologies failed in lowering the leakage current level, and the rest succeeded in reducing it to acceptable levels. Two of these topologies, the virtual DC and the multilevel half-bridge, were able to completely eliminate the leakage current. The multilevel half-bridge topology overcame the problems faced in the virtual DC-based one. Therefore, it can be an excellent selection for a single-phase system. As for the three-phase systems, some of the topologies failed and the others succeeded in lowering the level of this common mode current to acceptable levels. However, to the best of our knowledge, none of these topologies was able to completely remove the leakage current. Therefore, the aim of this work is to find an inverter structure that can completely eliminate the leakage current in a three-phase system. This is achieved by extending the single-phase multilevel half-bridge topology to a three-phase system. The proposed topology is characterized by a simple inverter structure, can totally eliminate the leakage current, it's able to generate multi-level output, and is based on a simple modulation technique. This is the selected single-phase topology where we have three-level inverter and it can be modified to operate at a higher level output. This inverter consists of two parts, switch 1, 2, and capacitor C1 forming the first half bridge, switch 3, 4, and capacitor 2 forming the second half bridge. Let's discover now how by implementing this topology we can totally remove the leakage current. Referring to this previous circuit, it can be graphically proved that by directly connecting the PV negative terminal to the neutral point of the grid, the stray capacitance will be bypassed, leading to a zero leakage current. We can also prove this theoretically by showing that the total common mode voltage is cancelled. In this topology, the inverter has an asymmetrical inductor distribution where L2 is equal to 0, leading to a null voltage at terminal 2. Consequently, the following equations are obtained. Thus, the leakage current is totally eliminated since no variations will occur in this zero total common mode voltage. This three-level inverter topology can work in two modes, 1 and 2. In mode 1, C2 is charged to half of the value of the DC input voltage. This leads to a three-level output, VDC over 2 minus VDC over 2 and 0. However, in this mode, the inverter acts as a half-bridge inverter, so it requires an input DC voltage which is the double of that across C2. In mode 2, C2 is charged to the same value of the input DC voltage, leading to a three-level output VDC, 0, and minus VDC. However, in this case, C2 is not naturally balanced. To solve this issue, we can see that there exist two switching states that lead to a zero output voltage. In the first zero state, S1 and S4 are turned on to charge the capacitor C2. In the second zero state, S2 and S3 are turned on to conserve the net charge of the bypass capacitor C2. In this way, the capacitor becomes balanced. Let's look now at the system elements. Using Matlab Simulink software, a Trina solar PV array is used. So in order to work correctly, it must be fed by two inputs, the irradiance and the temperature. Here we have the proposed three-phase inverter, where three single-phase inverters of the desired topology are connected to each other, and the negative terminal of the PV panel is directly connected to the neutral point of the Y-connected AC grid voltages. The module capacitance is obtained using this derived formula, and the grid voltages are operating at a frequency of 50 Hz with a voltage equal to 120 volt. In the inverter controller, a maximum power point tracker is used based on the incremental conductance technique. The control is based on the synchronous reference frame concept, where park transformation is utilized in addition to a proportional integral controller with the following transfer function. A phase locked loop block and a DC voltage regulator block are added to the inverter controller. The control strategy of the inverter differs between mode 1 and 2. In the first mode, the control of the inverter is very simple since the voltage across capacitor C2 is naturally balanced. The conventional sine pulse width modulation technique is utilized in mode 1, and its output is used to generate the appropriate switching gate pulses for the inverter. In the second mode, the control strategy is modified in order to maintain the voltage across capacitor C2, which is not naturally balanced. The control strategy used in mode 2 is illustrated in this image, where the flow diagram is applied to generate the appropriate switching gate pulses for the inverter. In order to check the validity of the proposed topology, the three-phase inverter is simulated on both mode 1 and 2. In mode 1, the PV array generates 400 volt, and the capacitor C2 is charged to half of it, 200 volt. The plots of the output voltage and the voltage across capacitor C2 are shown here, V0 in blue, VC2 in orange. When the PV array generates 400 volt, C2 charges to approximately half of it, 200 volt. This leads to a three-level output voltage varying between VDC over 2, 200 volt, 0, and minus VDC over 2, which is minus 200 volt. Same for phase B and phase C. The three-phase output voltages are delayed by 120 degrees to each other, leading to a balanced output. Also, the inverter of this PV system is operating at a unity power factor where the grid current is in phase with the output voltage. Same for phase B and phase C. In mode 2, the PV array generates only 200 volt now, and C2 is charged to the same value of it, which is 200 volt. This leads to a three-level output voltage varying between VDC 200 volt, 0, and minus VDC minus 200 volt. Similarly to mode 1, the inverter is also operating at a unity power factor. Same goes for phase A and phase C. To sum up, this proposed multi-level three-phase inverter can be considered as a promising topology in three-phase application, since it showed satisfactory performance. This proposed topology has simple inverter structure. It can completely remove the leakage current in a three-phase system. It can generate multi-level output and can implement simple modulation technique. Thank you for your attention, and I'm ready for your questions.